All right, thank you very much. So I'm Richard Johnson. I am the manager for the vulnerability development and research team that was formerly part of SourceFire VRT. We're now part of Cisco and under the banner of Cisco Talos. And essentially what we do is we work in cooperation with the rest of the teams who are responsible for putting content into the IPS, the malware engines, the spam filtering engines, things like that. And we find zero-day and third-party vendor products. We put that content, that protection into our products, and then we go talk about different research techniques and whatnot to try to elevate the level of technology available for finding bugs. So I focus on automation systems primarily, things that analyze programs that analyze other programs. And so we'll talk a little bit about that. My talks over the last couple of years at other conferences have been on fuzzing engine design. So ways to instrument processes such that you have a feedback loop and kind of novel techniques for causing programs to go down different execution paths. This is a talk that's more about how to take those engines, whether they're off the shelf or custom engines, and get the most performance out of the resources you have. Because at some point when you go from prototyping a unique trick, at some point you want to deploy that long term so that you're running as a fuzzer, all year round. And sometimes you can tune your systems properly or tune your engines, and we'll break it down basically into targeting and input selection. So that means your actual software target itself, and then the inputs that you're creating to try to cause those crashes. And we'll look at engine designs and how they've been fine-tuned over the last 10 years or so, and what techniques you can use to make your engines run faster and be more effective. And then finally at the end, we'll wrap up with a kind of overview of how to tune your hosts that you're actually running the fuzzers on. So essentially, fuzzing started quite a long time ago by accident. In the 70s, Barton Miller, he coined the term. But it got to be more widespread around the 90s when people started to fuzz environment variables and your arguments to your programs and things like that. And then we saw frameworks come out that would allow you to encode the structure of your file formats or network protocols specifically so that you would be making structured objects. And those structured objects took a lot of manual effort where you're reading an RFC or or the protocol specification and then translating that either into code or some sort of templating library using XML or some other form of grammar to represent that. Well, as machines have become faster and people wanted to put less upfront effort, we've switched over to mutational fuzzing primarily, at least as one approach that pretty much everybody can get into without a lot of effort, and also as even if you're going to go to the effort of describing a protocol or format, you might as well set up a mutational fuzzer while you're putting in the time that it takes to encode the protocol itself. So they work in hand, but once people got turned on to the fact that you could essentially, take an engine such as Radamza or other like Minifuzz and things like that, ZZUFF, and various other fuzzing engines that require very little configuration, just a set of example files, and then it will go mutate those. People kind of started to get lazy and didn't really think about how can we take this one step further and optimize that process. So we end up having more people fuzzing, which is great, but a lot of the resources that we put aside for fuzzing are wasted on things like, if we wanted to go fuzz Microsoft Word today or Adobe Reader today, most people would actually just go download the software, get a whole bunch of PDF files or Word documents off the internet, and then randomly mutate them and then run it, from the command line straight up. But we can do it a little bit better. So what I wanted to do is take a look at the problem from both a quantitative analysis of the fuzzer designs, meaning what is the performance that we're actually getting, what are the characteristics and the theoretical limits of each kind of part of the functionality of a fuzzer, and then qualitatively determine, are we selecting the right input set and are we using the right mutation strategies to produce the most bugs possible. So if you were to go look at some guidance for fuzzing, there isn't a ton out there. There's been about 3 books written, but you might start somewhere like the Microsoft SDL verification guidance. And this came out sometime in the mid-2000s, I think 2005 or so. And it put in their software development lifecycle for the first time a requirement to do some fuzzing, which is great. They had a very minimal guidance into how to do this. They supplied a couple of tools to their developers. I used to work at Microsoft, so I have firsthand experience with this. But this is essentially the complete guidance, this one paragraph right here. There are a couple of clues in here that are interesting. They do talk about an optimized set of templates, but they don't really define what that means. They say that it can double fuzzing effectiveness. That's really a amorphous claim without having any sort of qualitative or quantitative data to determine whether or not that was turning into bug finds. And then finally, they kind of picked this number of 500,000 iterations. But the question is, how did they resolve that should be 500,000 iterations when you're going to have different complexity of parsers, you're going to have you may have compression algorithms as part of your file or network protocol. These things will be wasted execution time. So obviously, it's going to be bounded by the practical resources you have available, right? Do you have a fuzzing cluster? If you do, how many cores do you have available? How much RAM do you have available? So they needed a reasonable limit. But without taking into account the actual target itself, it's really hard to put a discrete number on how many iterations you should be doing. And not only that, but we'll talk about how the cost of each iteration is so high that really what they were thinking is, well, we have this much time in a product release cycle, and if we need to test new components before we release it, it really comes down to a time cost, not a iteration cost. So I think iterations is a pretty poor choice if you're going to try to give guidance to people about how to perform fuzzing. So there aren't a lot of externally available statistics that you can read that would give you an idea of how people are fuzzing. More recently, Google did just give a talk last year on their cluster fuzz management system, but it doesn't have a lot of detail about what they're using behind the scenes, the actual engines. They talk about how they manage their cluster. The data that is available comes from Microsoft Windows Vista release time frame, where Microsoft says that they spent about 15 months or so, did 350 million iterations across 250 file parsers, and found 300 bugs. So, those numbers, we'll talk, and I'll show you kind of the numbers that we're achieving now, but those numbers nowadays, by my analysis, seem to be off by quite a bit. Number one, you're not producing a lot of bugs. 300 bugs across 250 file parsers seems pretty low, right? In my experience, we've found thousands of crashes in some of the most commonly used libraries for parsing images and movie files and things like that. So it doesn't seem like their strategy was very effective. And then to only be able to do about 350 million iterations over 15 months is not a very high rate of being able to execute and test the program. So the next data was for Microsoft Office 2010. It was slightly better. It seems as though they had a better strategy because they found more bugs. And I don't have a timeline on this one, but they did 800 million iterations, which is, significantly more than what they put into the entire Windows Vista operating system. And then finally in 2010, Charlie Miller did a talk about, which really brought back the resurgence of basic generation or mutational fuzzing, because he wrote a really simplistic fuzzer and used really simple tools and was showing that he could still find bugs in major file formats. And this is after the major push for Microsoft Office 2010. This is after Microsoft had rolled in their own fuzzing strategies. So there's clearly a gap in effectiveness there. So his design was he used just a 5-line Python script. I think I have it on the next slide. Microsoft has a free fuzzer that you can download along that's hosted up with their guidance and called MiniFuzz. And it's just as stupid as the algorithm that he has. It was basically pick a percentage of bytes in the input, a random window of bytes that it will change, and then mutate them randomly and just basically add static to the input signal of the real file. So he did find a number of bugs. He started out with 80,000 PDFs. He used a algorithm to run each one of those PDFs under the target and then determined what the code coverage was of each input file, and then did a min set of which of these files are required to achieve the maximum code coverage with the least amount of files going in. So yeah, in about 3 weeks, using just a 5-line Python script and Apple script instead of something like Bash to iterate, he was able to find quite a few crashes. However, his results were still, he was waiting 8 seconds for every iteration of opening these files. That's insane compared to what I'll show you in a minute. So now we know what data is out there. How can we actually break down this problem and really think hard about optimizing each different step? The first thing that came to my mind was, well, target selection. And, there's the first decision you have to make is, am I going to be targeting the 32-bit version or 64-bit version of the application? And while that might seem like a very trivial choice, there's a lot of things that are non-intuitive about the speed and execution of a binary, whether it's 32-bit or 64-bit. Obviously, 64-bit binaries are larger, and if you install like a 64-bit version of your operating system or application software, it's going to take up more space on disk. So if you're limited on disk space, that might be a concern. Your runtime memory usage is definitely going to be more, so that's definitely a concern for most people. The RAM's pretty expensive still. And there's basically going to be some software that only comes in 32-bit, some that's only there's some techniques for fuzzing that will only be able to be run on a 32-bit because it's using complicated introspection and debugging into the runtime process, and so on. And also, it's difficult to gauge exactly what the performance speed will be because it's really up to the compiler to utilize the extra registers in 64-bit architecture that are available to make up for the fact that it has larger pointer size and takes up more space and obviously has to navigate more memory. So this turned out to be a bit of a wash. This wasn't a very interesting topic to begin with, and the data out there is not very solid. Chrome says that essentially it's a negligible effect on their installs. Photoshop seems to claim that there's an 8 to 12% speed increase in execution under 64-bit, and the first data I could find dates back to old Sun Spark, and they said that 64-bit was a lot slower. So that's pretty inconclusive. It's going to be software dependent. At most, maybe we're going to shave 10% in time, which is, these are all going to add up as we go through and analyze these different tricks and techniques, but this is one that I pretty much set aside as something that we're not going to resolve as a general scope. So what's more important is that rather than worry about how big your binaries are, how do we reduce the actual code that we're trying to explore? So once again, we don't want to wait for the GUI to pop up and, for 50 libraries to load into your address space from the linker every time. And, that whole process of initialization is wasted time that you're not using to find bugs. So it's much more important to target libraries directly. And we've even gone to the point where we'll reverse engineer the interfaces to APIs and write thin wrappers directly for proprietary libraries that don't have functions exported necessarily. So this is where you start to add in a little bit more time in the upfront, and it's not just a fire and forget necessarily, but once you do a little bit of legwork, it's going to be a much more effective strategy. I mean, it kind of starts sounding like you're going to be doing unit testing, but ultimately this does pay dividends when you do fuzzing. And then the other thing you should think about is if your file formats or your protocols do incorporate some sort of compression or checksumming, you're going to want to nullify that. So essentially, if typically let's say you have a PDF file, a lot of those sections are going to be compressed as different sections in the PDF file. Number one, you can tell it not to use the deflate. You can actually put the raw data there if you add a different header to it. Or if it wasn't PDF that didn't have that functionality, you could just nop out the call that would normally decompress it and insert it into the file raw as the data that you want to mutate. And this turns out to be great because then you don't have to write a wrapper for post-processing your data after you've modified it to fix up checksums and skip compression. So this will also be application specific, but it tends to be a high impact modification. So if you put the resources in, or if you put the time in to disable these features, it pays off. There's a tool, if you're targeting Linux targets, that was released back in 2007 from Will Drury and Tavis Ormandy called Flare. It's a Valgrind plugin based upon the memcheck plugin, which does data flow analysis. And it lets you essentially tag different APIs and disable them using Valgrind, and then it outputs a file that you can pass on to GDB. So you do your analysis once, you figure out your points that you want to hook and skip over, and then you feed this file to GDB, so then when you run it, you don't actually have to modify the binary directly. You can simply run it under the debugger, and it will do lightweight skipping as that functionality. So it's pretty cool. It allows you to use the power of Valgrind and then the speed of a normal debugger. So that's great. So the next thing we need to look at, once we've figured out our targets and we've primed our targets to not be wasting cycles, then is how do we pick the right inputs to start with? You know, it typically would be that we just go to Google and download a sample set and say, all right, let's go. But really, you need to think of input as a numerical set, right? And so the larger that set of data is, the search space is greater, and if you're using a mutational approach, then that means that the data space in total is going to be, the efficiency of your mutation is going to be dependent on the total size of the file. So in short, you just want the smallest file possible that will reach the functionality you're targeting. DJ Bernstein actually wrote a pretty seminal paper a long time ago that talked about how protocol parsers and file parsers should be considered state machines. And this works similarly if you're more familiar with like the reverse engineering aspects or like code coverage metrics. But essentially, you think of the entire program as a state transitional space. And you know, as you go from parsing one functionality, then you're moving into different states, and that's all dependent on the memory and the inputs that you give it. So there's a paper that was released last year at Langsec, which is coming up here in a month, run by Sergey, and I think Travis is involved as well, that was written last year by Robert Graham, and they actually implemented a DNS protocol parser using the finite state machine. And for the first time, they kind of proved that it's possible to use FSM techniques to efficiently parse a network protocol. People haven't really paid a lot of attention to it in about 20 years because they thought it was too slow. So that goal is very similar, that model of the state machine is very similar to what we're trying to achieve through modifying our inputs. So we want to optimize for time that it takes to reach different states. By minimizing the file size, you can also target specific parts of the application. So it might be easiest to think about this in the sense, like if I was to write a little JavaScript that interacted with some certain objects, then you know that you're going to be fuzzing those objects. So when you think about larger binary file formats, you should think about it the same way. You know, you want to target the new functionality or the things that have perhaps had bugs before, but people haven't looked at in a while, and now you have this new fuzzer engine that can get deeper or use a feedback signal or something like that. So by isolating the functionality you're interested in, you're not wasting time on features that are unlikely to be security relevant and things like that. So once you if you do go with a larger corpus that you're not generating yourself, then the min set approach is valid. It's funny though, because if you've ever used the fuzzing tool Peach, it came with a pin tool plugin that was called min set, which didn't actually implement a proper greedy set cover algorithm. So actually Carnegie Mellon last year came out with a paper and tool called cover set. It analyzed about 5 or 6 different algorithms, trying to optimize for time, size, completely random sample set, a hot set that was based upon the number of bugs found by a specific seed before, reincorporating known crashing samples and using it as part of your mutation sample set. So anyways, the results of that was essentially that minset isn't nearly as effective as people think. It's almost actually equivalent to picking a random sample set if you're not optimizing for features and functionality. But they do have a current free implementation out there. You can go download it, read the paper. The one thing that Charlie did do well, even though he had an intentionally naive approach to fuzzing, was he did have a proper working minset algorithm. So for his approach, at least, he wasn't trying to design the world's best fuzzer. He was trying to show that simple techniques do still work. So now we've isolated part of the programs that we want to target. We've kind of thought a little bit about the inputs that we want to manipulate to begin with. The next thing to think about is how are we going to manipulate those inputs? And that comes down to the engine design. About 5-6 years ago, if you thought about what goes into a fuzzing engine, you might have thought, well, we generate the new inputs, then we execute the target with the input, and then we see if it crashes, right? Simple. But really, now we have better techniques now that allow you to trace the target while it's under execution, and that will bring a feedback signal to your fuzzing engine itself, and it will know that if the mutation it just did reaches new code, then that's an interesting input, and that's a new input that we can mutate again in the future and see if we get to other locations. So obviously we need to instrument the target if we want to gather a trace, and then we need to have a way for that trace to be real-time parsed and gather that signal out of the trace. And then also we need to detect not only failure conditions but non-failure conditions. The simplest example of this is if you open a file in Acrobats or whatever it might be. If it's corrupt, oftentimes they'll catch that it's corrupt, it'll show a little dialogue, it'll sit there for a while. And the old strategy was, oh, well, if it sits there for 5-6 seconds, let's kill it and move on. But really we can do better than that. We can look at the CPU timers and determine whether or not there's any load on the CPU. And so this is how we get many, many more iterations per second, is by having a better analysis of what is the system doing while the fuzzing is going on. So when we start, and then the final part, of course, is the actual mutations, the algorithms themselves that you're using to manipulate the inputs. So I can't actually see the crowd very well, but from a show of hands, has anybody here used American Fuzzy a lot before? You guys heard of that? Okay. What about Redamza? No? All right, so these are the two fuzzing engines that I use that are off the shelf. I'll give you a quick description of these. Essentially, Redamza, it comes out of a university in Finland. It's the guys that turned into the company Codenomicon. And essentially what Redamza does is it allows you to take a large set of input samples, and then it actually concatenates them all together, and then it looks for patterns that are similar across inputs and files, and then it generates new files that have the same attributes and properties, essentially. American Fuzzy a lot, we'll kind of briefly go over the actual algorithms they use, but its interesting trick is that it came with a compiler plugin. So when you compile an open source project with American Fuzzy Lop's GCC wrapper, it actually adds in a hook for every basic block. And this is a very simple hook that essentially records, it assigns a numeric value to every basic block, unique number, and then it XORs the previous block with the current block. What this is it's a state transition, right? You've taken a branch in the code that's based upon a condition. If this, then go to this block. So it has a way to provide a feedback signal, and that signal is as simple as, did we reach a new state? Because that's the most important thing. We are going to assume that we're going to run millions and millions and millions of iterations, so we don't really need to know much about what caused that state or any properties of that state. We just need to know that this input caused a new state transition, and so therefore this was an effective change to the file that allows us to explore more of the program. So this is a key component that up until about 2 years ago hadn't really been incorporated in any fuzzing, and this is a major game changer. But really quickly, the mutators that they do have is at every bit offset, they'll flip bits. At every byte offset, they'll flip bytes in different, D-word, short, 16-bit, 32-bit size. They will inject, at every byte offset, they will use boundary values for things like signed integers. You might use a null or a decimal 127 or 255, things where if they're used in addition or multiplication would lead to things like integer overflows, right? Then they do a deterministic for every byte offset. They do a series of manipulations, which once again goes back to you need the smallest input size possible because you're going to go through all of these for every byte that's available. And then it switches over to doing keywords that you can supply. So if you're targeting, let's say, a QuickTime movie format, they have little ASCII 4-byte tags that are at the header, part of the headers of the structure of different frames of the movie inside. So rather than having a fuzzer try to randomly come up with these new frame names, which is a 1 in 4 billion guess, you can supply a list of possible tags, and it will cycle through the file and add those tags in and try to get different sequences of bytes interpreted as different internal data structures. So that leads to interesting crashes scenarios as well. And then finally, it resorts to what it calls havoc, which is like the Charlie Miller approach, which is pick a random set of bytes and modify them and just continue that forever. And then every once in a while, go ahead and splice two different inputs that you've generated before together at an arbitrary offset. So that's the approaches AFL takes. Redamza, I won't go through all of them because as you can see, there's 3 pages of these. But actually, if you were to read through these, they're very similar. Basically, what Redamza adds is a lot more interpretation of ASCII type data. So it will find delimiters such as XML or XHTTP, brackets, or things like patterns that are common delimiters, essentially, or even if it's not a known delimiter, if it's a arbitrary delimiter that some protocol determines is a good idea, it will recognize those automatically as well. I got turned on to Redamza quite a while back, like almost 10 years ago now, and they were really, really cool because they had some functionality that they've since taken out because they were too expensive of operations, but they were very novel techniques, things like using n-gram analysis and using like the way that compression algorithms work, right? They try to tokenize your input so they can make a short form that describes what the decompressed data looks like. Well, you can use that as well to take a short form of what your input looks like and then modify that a little bit. And then when you decompress it, you end up with a jumbled output. Really cool tricks. They even had automata as well that would travel through the input, using different techniques to modify the input at will. But like I said, they took that out because they found that doing more iterations in their more random set was more or less just as effective and less complicated. So what we can learn from these two is that if you're going to you should use a deterministic set of known boundary values and things that are commonly going to cause crashes if there isn't much robustness in the code for integer overflows and misinterpreting sign values. And then you should also not really have an end state to your fuzzing. You should be able to run a fuzzer and go on vacation for 3 months and come back and have it still running and producing crashes. You shouldn't have to babysit it or say, oh, this file's done, I better go find a new one. There should be a way to look at a sample set and continuously try to come up with new creative ways to find bugs out of it. And the only way that we can figure out this, the quality of the mutations, is by adding that feedback loop that AFL did. So assuming that we've now picked one of these two engines or your own custom engine that incorporates this strategy, the next thing we need to do is execute the target as rapidly as possible, right? And that's not only what I was talking about earlier where we want to isolate the code, but actually literally reducing the overhead of executing a process over and over and over. Now, the way to do this, what we want to do is skip the linking. Like I said, if you have 100 megs of binaries being mapped into your process space for every iteration, we can skip over that, skip over the libc initialization. We can skip over the cost of creating a new process address space, things like that. And the way to do that is by using a fork server. Fork servers allow you to essentially copy the process near instantaneously on Linux using copy on write pages. And if you're not familiar how that works, essentially, rather than creating a whole new process with its address space that it's loading binaries into, it creates a new virtual address space, and virtual address spaces for your processes are managed by the kernel through a data structure that maps real physical RAM into this virtualized address space that you have. And so all it needs to do is copy a very simple data structure for the Linux fork implementation to clone that process and continue execution right from where you were. On Windows, unfortunately, and OS X, they don't have this functionality. It wasn't part of the kernel architecture. So there is no technical way to skip the populating new pages in the new process. But I got turned on to what used to be the Unix subsystem, POSIX subsystem inside of Windows a little while back, but they somewhat removed it, and it's only supported in enterprise editions, and there's just basically a lot of hoops to go through. So the fallback was to look at Cygwin, because that's a POSIX implementation for Windows, or MSys, which is supposed to be a minimalistic POSIX implementation that was forked from Cygwin. And I was reading through the Cygwin archives from about 2007 or 8, and they had mentioned these two APIs, RTL clone user process and RTL create process reflection. They're undocumented, non-exported APIs that, as far as I could tell, nobody really has a working implementation for them. So we took that out upon ourselves to try to figure out how can we increase the speed of creating a new process in Windows such that we can get it closer to the Linux approach of just updating page tables. Now, one way you could do this, of course, is you could write a kernel driver that completely implements an entire new process creation paradigm. But we went ahead and went with the kernel driver, the kernel code that's there, and just try to utilize it and fix up the process as needed. And I'll show you what happens. Oh, where's my, okay. Well, this is the demo. We'll go back to the results in a second. So here's demo number 1, forking demo. Oh, right. We're not mirrored. Okay, so for the first demo, what we're going to do is we're going to look at the speed of forking on various operating system, on Cygwin, on MSys, and then our own native NT API fork implementation. So if we do a quick fork of about, let's say 500 iterations or so, this is running, I can show you the code here. This is running a very, very simple function. All it does is, because what we're trying to do is reduce the cost of fork itself. There is no load on the child process other than process creation and then an immediate exit, right? So right here, this is the parent body. All it does is it takes the time of day before it starts its loop. It waits for the child to exit. And then the child body is right here, it just exits. So we're simply creating processes as fast as possible and then measuring the time to get a metric of how quickly we can fork. And so we can see here for 500 processes, it takes 2-3 seconds, something in that time frame for this is Cygwin, right? So let's go see what MSys does. Do 1,000 there. Now, we predicted that MSys would be faster than Cygwin because it's a minimalistic implementation. It doesn't have as robust of a fork implementation as Cygwin does, but it turns out that it's slower. And so we went to investigate that, and they have not changed the fork API in MSys at all since they forked it in 2004 or something like that. So it's actually using less code, but less efficient code in its algorithm. What it looks like what happened was the processes were initially created in a suspend state, and then a bunch of stuff was fixed up and then continued. It manually copied the pages over and things like that. And then later on, Cygwin realized they didn't actually have to start suspended, so they allowed some of the initialization of the process to occur while it was still writing to the process memory. So it's actually about 50% faster or so. But we can look at our version, which is slightly different code. This is the minimal fork, and I can show you. Essentially what we did is we took the same code right here, and instead of using the POSIX fork functionality on this line, we had to implement using the NT create process API, which is going to be buried in my resolutions low. So I'll just show you the timing on this real quick. And I've got these numbers in a slide that we're coming up with in a second. I just wanted to show you that I wasn't making up numbers. And we'll see that that one's twice as fast as the Cygwin timing. So if we blow this up to a larger scale of iterations, you will see that essentially over 10,000 iterations, Cygwin does that in about 46 seconds. which gives us about 213 executions per second. MSys is almost twice as slow as that, so we certainly don't want to use MSys as our shell and whatnot if we're trying to port over anything that's going to use a rapid forking. Linux, which is the benchmark that we're trying to achieve, which is incredibly fast because, like I said, it only has to copy the kernel data structure and not actually copy into the pages itself, is extremely fast, 4,500 executions or 4,400 executions a second. But the native implementation that we wrote, which is the first one to exist so far, it's a novel creation that will open source pretty shortly, is twice as fast, even 2.5 times faster than the Cygwin. So while we are still 8 times slower, 9 times slower than Linux, we've gone from being 22 times slower down to 9 times. So we've certainly increased the functionality, the ability to try to take the same approaches to the Windows platform. So this is a significant win from my perspective. Okay, so the feedback looping that AFL implemented required the compiler plugin, like I mentioned. Now, it's been a known need for a long time that we need to get some signal back out of the fuzzing system itself, but the previous implementations were done somewhat naively, but also sometimes just simply limited to the overhead of a binary instrumentation system, right? So PyMay was one of the first ones that allowed you to do code coverage, and Jared DeMott's evolutionary file fuzzing system was released back in, I think, 2006 or so. Roger did some genetic fuzzing that I think he's probably spoke with some of you about in the past. Jared DeMott was one of the first people to do that in the academic world. Unfortunately, he built it on top of a somewhat cumbersome system, and so the performance wasn't where it needed to be to allow his algorithms, I think, to come to fruition beyond proof of concept level, right? Nobody I know is deploying EFS at scale and finding bugs with it. And that's simply a platform issue, and you know, Roger could speak more to the algorithmic level, but ultimately it wasn't the right answer. Last year, a binary version, very similar to EFS, but it was built on top of Pin, was released from Cosync, and that was a tool called, I think, Blind Code Coverage Fuzzer is what the BCCF stands for. Unfortunately, that's also quite slow. It's workable, but it's going to be about 30 or 40 times, maybe 50 times slower than standard execution. So you're kind of kicking yourself or shooting yourself in the foot. You know, you have to buy 50 more machines to get the same fuzzing speed and the same, you know, iterations back out. So I don't know if it's really worth it. Interestingly, HongFuzz uses the branch trace functionality of your CPU. And if you don't know what this is, it's like if you do a single step in a debugger, that's using a hardware trap. So your CPU itself flips a flag or looks at a flag to determine, do I continue running every instruction or do I just run one instruction? Well, you can set a internal register, set some flags in an internal register in the CPU from a privileged mode that converts the single stepping into actually a branch stepping. So that means that it will execute until it gets to the next jump, essentially. And this is the resolution that we need for the code coverage feedback that's similar to the signal that AFL gives us. So it's interesting, but unfortunately it's also a little bit too slow. And then of course the problem with AFL is it's source only. Well, when it came out, it was only targeting source code. So we were looking for a solution where we can target proprietary third-party software and ideally bring this to Windows, but certainly we want to target things like enterprise software that typically, even on Linux or OS X, is not released in open source form. Okay, well, I started 10 minutes late, so I'm going to go a little bit extra. I have 2 more demos, so you guys are going to want to see these. So anyways, the hooking engine selection is highly critical. Pin and Dynamo Rio are typically what people go to if they want to instrument a program on the fly. But we wrote something that speeds up Pin and Dynamo Rio if you want to use those type of tools in an iterative fashion. So this applies to if you're doing code coverage to do a min set, if you're using some of the techniques that I was talking about last year for concolic execution. Anytime you need to trace tens of thousands of files under a pin and run a same program over and over and over, you can use our tool, and I will demo that now. It's a wrapper for pin that uses LD preload functionality to inject a fork after the initialization of pin itself. this one. So what I'm going to show you, since it's difficult to deterministically find a new bug on the fly, I'm going to apply these techniques to a concolic execution engine that will crack a password on the fly, assuming my operating system comes back. The trick here is that pin is a runtime. It's like a debugger that sits inside your process, and it manages the linking and execution code itself. And so when you branch to a new part of the code, it will copy that into a code cache and allow you to inject callback hooks to modify the code on the fly. And so that takes, oh, God dang it. That takes a lot of time because it does a full disassembly. Sorry, the screen resolution is really crimping my style here. Okay, so what we're going to start with is an empty serial.txt, and this is going to be expected to contain an encrypted key in this algorithm that we're going to automatically solve. So this is the key. It's basically XORed with value, so it's a simple encryption, but the idea is to show how we're going to run over this function 27, 28 times to solve the password, and what's going to happen is a pin tool is going to trace it and actually follow all the data flow and automatically determine how to reach the next loop. So it has a feedback signal that says that yes or no, this is the correct character in the password or the serial, and it's able to look at the comparison that's done on the key that's hard-coded in here against the key that's coming out of the file. So I'll show you what that looks like. Our tool will automatically populate the serial file and eventually have the final solution that you'll be able to watch it do iteratively. And first I'm going to run it with pin only without our turbo tracer injectable shared objects. And you will see over here on the left, it's off screen. Okay. So you'll see here that it's iteratively finding the serial number as it goes, right? So if you're looking at the bottom line here, it's saying, you know, this is my long serial, and it's discovering that by running over and over and over underneath of a pin tool that follows the data flow. It looks at the comparison, and what's happening is in memory you have the stored serial number that you're looking for. In the loop in the code, it's comparing what the byte of the file is, and if it's incorrect, then it exits, and it looks at what that condition was, like why it exited, and then it populates the file with something that will take the opposite branch and solve it on the fly. So this takes about a full minute. It's almost done here. And this is the tool by itself, and what I wanted to show you is that by injecting our fork server, we can increase this by about 2 times. So that took 1 minute, 12 seconds. If we run it with, sorry, I gotta kill this file real quick. All right, so now with our shared object injection, you will see that this will find it in a much, much faster time period. And this is due to us skipping all the overhead of disassembling the target process and just using our fork server to do it very rapidly. So you can see visually that it's solving it, you know, nearly twice as fast. The time output will come up here in just a second, and we'll be able to verify that. I did a talk specifically on the techniques of concolic execution last year. So if you're kind of confused what's going on the screen over here where it's doing the data flow analysis and solving that, you can talk to me a little bit later and I can point you at some more material that will explain it. But as you can see here, it came up with the same solution in half the time. So if you use pin tools, this is a way to speed up your execution time by about twice as fast. All right, so we're about to hit the third demo in just a second, because now that we've got the forking figured out, we've got our input figured out, we've got our targets figured out, we've figured out if we need a feedback loop, we can make pin twice as fast. We've made all kinds of great performance increases. So what's the last thing? Well, we still want to get these all tied together and working with AFL and using a binary targets as opposed to source code, right? So you can reference this later if you like. This is using different pin tools that you could go download yourself right now and see how it goes faster. The basic blocks pin tool will do a code coverage and that sort of thing. So there was one attempt to bring AFL to the binary world, and that was by modifying the QEMU engine so that QEMU would do basic block testing on the fly. That's out there, but it only works against static compiled binaries. It only works on Linux targets. And it's about 4.5 times slower than running it at native speed. So we thought, well, there's one more thing that we can do to try to speed up the technology that's available right now. We can go look at a platform called dyneinst. Dyneinst works a lot like it more or less allows you to not only modify the program in memory as it runs, like Pin or Dynamo Rio does, or Valgrind. Instead, it modifies the binary and then writes it back out to disk. And so that allows you to use the operating system's copy on write page mappings and not have to deal with additional calls into the code cache, and it eliminates any of the overhead other than the raw instructions that you're adding to bring that feedback loop out of it. So we wrote a tool for dyneinst. It's actually an interesting little anecdote. I know I'm short on time, so I won't go too deep, but Barton Miller, the guy that coined the term fuzzing, actually is still at University of Wisconsin. He's a elderly old gentleman now, the head professor, and he's the head of the dyneinst project, just out of pure coincidence. So I find it interesting that now I'm talking to the guy that more or less invented fuzzing by using his binary instrumentation system to feed it back into a fuzzing loop, so it's kind of cool. So the results that we see here with this approach is actually that we can target binaries with only a 30% overhead, which is until now more or less unheard of in any instrumentation for doing fuzzing feedback and things like that. So I will show you that real quick, and then we'll wrap up in just a second. This one. Okay, so this is going to run AFL. This one is going to, so AFL by itself against read PNG, which is a default test tool that comes with libpng to parse PNG files on the fly. What we're looking at, what we want to pay attention to here is the execs per second, really. This is a fuzzer that we've found bugs in libpng with. This is the AFL that I've been mentioning. It's really cool. You can go download it. But what we're trying to do is get a benchmark of the native compiler instrumentation versus QEMU versus our dyneinst. So we can see here we're getting roughly 1,200 or so iterations per second. So let's go over and see what we'll get with that with QEMU. You can see that it's slowed down significantly. It's about 230, 240. So that's the implementation that was available to target binaries, static binaries. That's part of AFL. And then here's our new static binary rewriting approach, which will land somewhere in between and get as close to the original source instrumentation speed as possible, but still being able to target binaries and including dynamically linked binaries. So there aren't any restrictions on the binary target really. And we're working right now to try to port this to Windows. So this is the last crucial step, is getting the static binary rewriting functionality working on Windows. And right now, the only missing piece in that is that their disassembler is highly tuned towards GCC, so it doesn't recognize some of the compiler primitives that are output by Visual Studio. So they're coming out with a new version pretty soon. But yeah, you can see here, look, we're at 800 some iterations per second versus 1200. It's not too bad, right? 30% or so performance hit. So those three tools are essentially a state of the art right now. They have advanced the ability to do fuzz testing using these approaches. So the last thing is you need to bring out the traces in a sensible format. Typically what people would do is record all basic blocks hit and then post-process and diff and deal with a lot more data than they have to. By using the block tag, like the numerical block tags, and using the XOR, just the edge transitions, all that data can be stored in a bit mask. So it takes the XORed value of block 1 and block 2, the from and the source and target blocks, XORs them together, comes up with a single integer value. That offset in the bit mask determines whether or not that transition's ever been taken before. And when a new bit is flipped, then it says, all right, keep this input. We've reached a new state. It's very, very quick. It's done through shared memory and whatnot. Well, I know I'm running into somebody else's time, so I'm going to go ahead and pretty much skip over the stuff. It's, instead of using a heavyweight debugger analysis on your crashes, just simply use signals if possible, and then post-process later. You don't want to interrupt the fuzzing process itself. And then the summary for the host configuration is turn on all the system caching that you can. A lot of people start off fuzzing using their older hardware, and that's just fine, but you can still fine-tune your older hardware so that if you have spinning platters, you can use a USB disk to add a solid-state cache such that it will double the speed, actually, of your I/O. And I have some benchmarks in here that show the differences between spinning platter, RAID 0, SSD, and then finally, of course, RAM disk if you can afford it. So on our cluster, we're privileged enough to have enough RAM that we run all of our fuzzing at RAM disk, which avoids the disk I/O time because fuzzing is a high I/O activity. So anyways, I think I'll end here because I hit the most important bits, and I'll take a few questions if you guys have them before we move on. And thank you very much.